without further ado, let me introduce you to the man you're going to be hearing a bunch from today. Over 25 years of experience in the utility market. He is hands down has a tremendous amount of experience in everything utility, from substation design to real-time power trading to substation and transformer monitoring. He is a professional engineer. He's a member of the IEEE Power and Energy Society. This guy is definitely somebody you're going to want to pay attention to today. Without further ado, Leon White. Leon, welcome.
Thank you, Jeremy. It's great to be here, and I really appreciate everybody joining the webinar this morning. I think you'll have this morning, this afternoon, this evening, wherever you're at around the globe. We appreciate you being here, and look forward to providing a lot of good information. I've been in the industry a long time, and online transformer monitoring kind of started out with hydrogen monitoring. And as multi-gas monitoring became more and more popular, a lot of companies went into multi-gas, and a lot of focus went away from hydrogen monitoring and all the benefits that hydrogen monitoring brings. And so my intent today is to help people understand the benefits of hydrogen monitors and help them to realize that it's still a great technology. There's more and more hydrogen monitors on the market all the time, and so chances are your favorite vendors are offering some sort of offering for hydrogen monitors, and it really can provide a lot of benefits for your transformer fleet. So we'll go ahead and get started here. I'm going to try to leave about 10 minutes at the end for questions. And so, as Jeremy said, feel free to put in a question. If you have known me in the past, normally I don't have a beard. I have been growing a beard the last couple of years. I said I'd have a little joke about Santa. I hope Santa brings everyone a nice hydrogen monitor for Christmas this year. So anyway, here we go. Okay, there we go. So for the agenda today, we'll be talking about, first of all, I found that a lot of people don't quite understand when we talk about a distribution transformer, an instrument transformer, or a large power transformer, what those mean. And so I've got a quick picture of those and just to kind of get everybody on the same page. And then there's a lot of different oil types. So we'll talk a little bit about the oil types and the popular oils today, and some of the challenges different monitors might have with those different oils. And of course, the primary reason for the webinar today, why is it important to monitor hydrogen? Then I'm going to talk about transformer gassing phenomenon and what's really going on in the transformer when gas is being generated, and how is that going on in real time, and what's the best way to monitor that. Then I'm going to go through a couple transformer use cases. I've seen over and over and over again hydrogen monitors alerting people to transformer problems, and as you get one or two saves under your belt, you really start developing the desire for more and more hydrogen monitors because you really see the benefits. Then I'm going to talk about various online DGA technologies. There's a lot of different technologies out there today, and I know a good amount about most of them. There's one that I'm still kind of weak on, so we'll talk about that. Then I'm going to look at some exciting things that some people are doing, some different vendors are doing around the world today, and looking at online DGA and transformers a little bit differently than has been looked at in the past. And so some really nice innovations and things that you probably haven't thought about. Then, since most of the transformers in the world are owned by utilities, I'm not sure how things are done internationally, but in the U.S., I'm very familiar with the accounting models and justification and some of the challenges to being able to justify online monitoring. So we'll talk about that. And then we'll conclude with what do you, if you're going to buy a transformer monitor, what are some of the things you want to think about? You know, having a great monitor out there, putting it on your transformer is a great thing, but now that it's there, how are you going to deal with the data? Who's going to deal with it? Is there maintenance involved? A lot of different aspects there that you want to make sure you consider when you're looking at online monitors for your transformers. So there are lots of different types of oil-filled transformers. There are other types of transformers, dry types and so forth, but if you're going to be looking at online monitoring of transformers, most of the time, well, DGA anyway, and hydrogen monitoring, there's going to be some type of oil inside. And when there's a problem in the transformer and things start heating up, that oil starts degrading, and hydrogen is a byproduct of that oil degradation, usually due to high temperature. So when bad things happen in transformers, that's when you start generating hydrogen. So whether you're looking at a large power transformer, large generator step-up transformer, those are usually the most critical transformers are the ones that get monitoring first. And then as a lot of people put online monitoring in their transformer specs, so the monitors come on the transformers from day one, and so that's a good thing, so you can monitor those transformers while they're under warranty. If you haven't noticed, a lot of things today don't last as long as they used to, so finding out about problems while the transformer's under warranty is a very good thing, so that hopefully that can get addressed before the warranty expires and you start having problems. So the beauty of online monitoring today, and especially hydrogen monitoring, is that regardless of the size of the transformer, whether you're talking a large transformer with 30 or 40,000 gallons of oil, or if you're talking an instrument transformer with a gallon of oil in it, the good thing is there are hydrogen sensors today that can help you help warn you to ensure that you're in the know about whether the real-time health of your asset there. And of course, nobody wants to wait till something to fail and possibly blow up, which is what usually makes the news and usually gets people out of bed and working long hours and so forth when those things happen. So, and then of course today you also have to worry about the environmental concerns of oil, burning oil and what's going into the environment, or oil possibly going off property and all those different environmental concerns. So for the different oil types, historically mineral oil has been the primary oil that's been in power transformers and all different types of oil-filled transformers. Naphthalate is normally what's used, but there's also paraffinic oils. Paraffinic oils have a higher amount of wax in them, and so they have to be refined to get that wax out because you don't want your oil glazing over. Silicone oil is popular in certain classes of transformers. Today, natural esters, which are essentially vegetable oil, and I've got a little note there for transformer consumption only. Even though it's vegetable oil, you don't want to be frying up your tater tots for dinner in the vegetable oil. Although I do understand, I haven't experienced it myself, but there are some of the oils actually do smell better than other oils. So I'm very used to being in the field and having that, coming home with that mineral oil smell on my clothes. But I do look forward to smelling some of the better smelling natural esters. So probably the most popular natural ester today is FR3. Then you've also got, I forget how you pronounce it, Midel or Midel oil. And there's been a lot of interest in Midel oil recently. Midel makes a natural ester and a synthetic ester. And if you look at the published Ostwald coefficients, so the Ostwald coefficients are the factors that tell you how easily the hydrogen, when the oil degrades, how easily does that hydrogen dissolve in the oil. And so if you look at the Ostwald coefficients, published ones for Midel oil, the synthetic ester, it's actually very close to FR3. So we're expecting that most people, if you're going to be using Midel oil, probably the online monitor that you're using, if it has a setting to set it for FR3 oil, then you would probably use that setting for the Midel natural ester. There's also ABB Biotemp. I've seen a little bit about it, but I haven't actually seen any of those in the field, so I don't have any personal experience with that. Midel also, as I said, makes a synthetic ester. We at H2scan, we make hydrogen sensors for a lot of the different monitors in the market today. And like I said, we've had a lot of interest in the various Midel oils that have recently hit the market. And so we just completed a week or two ago some extensive testing on the Ostwald coefficients for the Midel synthetic ester. And at least at lower temperatures, the Midel coefficients are very close to mineral oil. And so we're going to do some ongoing testing and confirm. It's looking like for the higher temperatures, there is some divergence. So we probably will include separate setting for the Midel synthetic if it's necessary. But it is interesting that these Midel synthetic and natural esters are actually, the Ostwald coefficients are very close to other popular oils. And so why is it important to measure hydrogen? Probably most of the people on the call have seen a chart something like this. If you look at hydrogen, it's not generally produced at very low temperatures in the transformer, so you're probably not going to see hydrogen if you're even getting up to around 80 or 100 degrees C. Typically, hydrogen is going to be generated in mineral oil, at least, starting around 150 degrees C, which is hot for you and me, but not super hot inside a transformer. And as the hydrogen, or as the temperature increases, you generate hydrogen at a faster and faster rate. As your temperature increases, if you're looking at the other gases in your oil, methane, ethane, and ethylene, your hot metal gases, those will start being generated. And of course, once you have arcing in the transformer, you also get acetylene. And so one of the misconceptions about hydrogen is people will take an oil sample and say, well, I've got these other gases, methane, ethane, maybe even ethylene or acetylene, but I don't see any hydrogen, so I don't think hydrogen is important. And that's a big misconception because typically utilities or people who own transformers are taking oil samples once a year. And hydrogen is the gas that will escape from the transformer the fastest. It's the smallest molecule, will escape. If it's a very tight transformer, then it actually will stay in the oil. And if there's a nitrogen blanket, will stay in the transformer a very long time. But especially as transformers age and they're not quite so tight and there's small leaks around gaskets or so forth, hydrogen will escape from the transformer. So typically what you see with hydrogen is when the hydrogen is generated, hopefully it's just due to a temporary event, overloading or something overheating very quickly, and that will lead to some amount of hydrogen being produced and possibly other gases. And then once that hydrogen's produced, if no more, if that whatever happened to cause that to be produced goes away, then then over time, normally the hydrogen will escape out of the transformer. And usually, if it's not a very tight transformer, that hydrogen will be gone very quickly within days. Usually that hydrogen will stick around at least a few weeks to a few months. And like I said, if you have a really good tight transformer, it will actually stay in the transformer for years. So it is a key gas to look at. And the great thing about hydrogen is there are a lot of low-cost sensors on the market. Like I said, hydrogen will tell you if there's something serious going on in your transformer. Again, by looking at just annual oil samples, I've had people explain it as if you're driving along, and today we have the Tesla, right? And so the Tesla, you don't have to pay attention, right? At least that's what some people think. And so when if you're not paying attention, you know, a lot of things can happen. So if you have the online monitoring, watching your transformers continuously, then when that hydrogen is generated, you're going to know about it. You'll be able to correlate, you know, did my fans not work? If you have large power transformers, you know that without any external cooling, you might have a 50 MVA transformer, but add a couple of good stages of cooling, and now that 50 MVA transformer is good for 100 MVA. And so if that cooling's not working and you're loading your transformer up to 100 MVA, you're certainly going to be generating hydrogen and probably some of these other gases. And so again, hydrogen can alert you to a lot of different things going on in your transformers. And so this is an interesting graph that I came across at a conference a few years ago, and it really helped me make sense out of the different gases that when people would show me their DGA reports, what was really going on. And if you look on a percentage basis at lower temperatures around, you know, and this is a relative thing, around 100, 150 degrees C, generally the primary gas you're going to see is hydrogen. And as the temperature increases, that's when you start seeing your methane, ethane, and ethylene increasing. And as those start dropping off as you get up to around 700 to 1,000 degrees C, you primarily get acetylene and lots of hydrogen. And so this graph, you got to keep in mind that this is on a percentage basis. So during that mid-range, your hydrogen value isn't actually going down. The hydrogen value's continuing to increase, but that's on a percentage basis. You're generating the other gases in higher concentrations than you are hydrogen. And so if you look at just your hydrogen trend, it will continue to increase on somewhat of a linear basis if you just continue to increase the temperature of the problem in the transformer. And so again, the faster or the hotter the issue in the transformer, the faster you're going to generate hydrogen. And so hydrogen is a great indicator of a significant issue in the transformer. And so what I found out is a lot of people don't really understand what happens in transformers when the gas is being generated. And so I came up with a little, I tried my hand at some animations in PowerPoint. And so hopefully this comes through okay. And of course the animations won't be on the PDF, but I hope this makes my point. And so let's see here. Okay, so you've got some problem inside the transformer that starts generating hydrogen. Okay, initially that hydrogen, of course, is lighter than the oil, and so it migrates up. If you've got a nitrogen blanket on your transformer, it goes up into the headspace of the transformer. Okay, and so the first place you're going to see that, and the fastest, is if you have a hydrogen monitor that's monitoring in the headspace. Okay. And so eventually, once there's enough hydrogen in the headspace, the hydrogen actually starts dissolving in the oil. And as your oil moves around your transformer, which varies based on ambient temperature, your your load on your transformer, how hot, what cooling you have on. A lot of different variables go into play as to how long it takes that hydrogen to reach equilibrium around your transformer and in equilibrium in the oil. One of the things you can do is, and it's actually getting to be more popular today than it used to be, because you used to not have online monitors, and so the primary thing that people did was took an oil sample, sent it to a lab, and got their DGA analysis, their dissolved gas analysis. But today you have monitors that can also work in the headspace, and so there are a lot of different test monitors out there, portables, that can actually pull gas from the headspace and analyze it and give you a total combustible gas, or potentially even just hydrogen if you're interested in that. But there are some portable gas monitors. So gas monitoring in the headspace is actually becoming more and more popular today. And then, of course, what most popular, probably 99% of the monitors today that are on transformers are monitoring in the oil. And so it's important to note, if you're measuring in the headspace, especially the hydrogen, the amount of hydrogen that dissolves in the oil, there's about a 20-to-1 ratio. So there's about 20 times more hydrogen in the gas space than there is in the oil. And so if you have a monitor that's calibrated in the headspace, you need to make sure it's calibrated at about 20 times what that monitor would be calibrated for in the oil. And so some monitors do automatically take that into account, because there aren't really any standards that I'm aware of for monitoring or giving you a good value, what's a good or bad value of gas in the headspace, but there's lots about DGA, and so they perform that calculation and actually give you an equivalent value dissolved in the oil. So whatever the concentration is in the gas space, they'll give you that oil calculation, and so you can use the various diagnostic tools available to determine if there's something serious going on or not. And it's important to note too that really most people are looking at the trends over time, and so IEEE just released the new C57.104, and it not only has the gas values as far as condition levels, but it also talks about rate of change, whether it's a daily, weekly, monthly, or yearly rate of change, and what values are that you should be concerned about of the various gases. So now I'm going to go through a use case. This is actually a very large transformer at 1100 MVA, generator step-up transformer in a nuclear plant. And this is about a month's worth of data. And during most of the month, everything's looking fine, right? You do have some gassing going on in the transformer. This transformer, from what I understand, was less than 2 years old. So to have some of these gases in there, of course, was not a good thing. The blue line is hydrogen. And if you'll note, this is on a logarithmic scale, so you can see what's going on around 1 ppm as well as what's going on around 1000 ppm. Okay. And so what you see here is early in the month, all the lines were flat. And as I said, if you're watching an online monitoring or an online monitor, if the monitor is showing that the gas levels are consistent, that means no new gas is being generated. There's not an active fault or an active problem in the transformer. Once your gases start increasing, that's the time for concern. And this, of course, was an 8-gas monitor on a very critical transformer, so it's easy to justify that. And if you look at the hydrogen value here, it's hard to see on the scale, but You can trust me that the hydrogen value went from about 30 ppm to almost 300 ppm in 2 days. And the primary reason for that is that acetylene started being generated. So acetylene pops in about a half a part per million on the chart there, and over 2 days gets up to about 4.5 parts per million. So when we generated just a little bit of acetylene, we generated lots of hydrogen. We also generated, at that same time, there was overheating, and in that 2-day period, there was significant amounts of other gases, your methane, ethane, and ethylene going up. But if this transformer had only had a hydrogen monitor on it, again, you would have seen about a 10-fold hydrogen increase in 2 days, from about 30 to about 300. And just to show you what happens when you have the online monitoring, this green line here, I hope you can see my arrow here, but the bottom green line, well, the middle green line, because there's another one down here, but this green line shows the load on the transformer. And so within 24 hours after this gassing event started, and it continued because the gases continued to increase, they started pulling the nuclear plant offline, and within 2 days had the plant offline. So because they had the online monitoring, they were able to react very quickly. This could have resulted in a complete transformer failure. And of course, you don't want to risk anything exploding in a nuclear plant. So you get it offline as soon as possible. And so when they did an internal inspection, they found this was the low voltage leads coming out of the winding going up to the low voltage bushings. And they found some overheated crimp connections, and they actually had found 2 problems. If we look at the next slide, we see when they peeled the paper off at the end of the leads, again, this is something to the effect, somewhere around 20,000 amps is the normal rating on the low side of this transformer. And so it, of course, was carrying a lot of current. There's 16 of those conductors connected to one bushing. To me, it's either 500 or 750 copper. So very large amount of current. And what they found is that the leads closest to the winding, you see the leads closer in the near ground in the picture, were all overheated. They were carrying a lot more current than the leads farther away from the winding, and so there should have been a flux shield in between the winding and the low voltage leads, so that you didn't have that situation of the leads, some leads carrying a lot more current than the other. The other issue they found, if we go back to the prior slide, is that they had wrapped too much paper around those leads. And so in order for the conductors to stay cool and those crimp connections to stay cool, the oil has to fully impregnate the paper. And when you're trying to keep those cool, if the oil doesn't fully impregnate the paper, then the oil is not pulling the heat away from the conductor. And so now what you've created is insulation to keep that heat in, and that was enough insulation to completely burn away the paper until there was no paper left. And once you lose your paper, then you've lost your insulation, and it started arcing. And so, of course, our online DGA monitor was able to watch that in relatively real time. Okay. And then the next case is this is a 500 MVA GSU. Now, in this case, they only had a hydrogen monitor. The hydrogen monitor went into alarm. Over a 2-week period, they took a couple, they took 3 oil samples over a 2-week period. By the 3rd oil sample, they were seeing acetylene. They did an internal inspection on the transformer, and the manufacturer sent somebody out, and the guy was in the transformer for about 2 hours, couldn't find anything. And then on his way out of the transformer, happened to notice that crimp connection, that termination again at the low voltage lead. At low voltage, you have much higher current than at the higher voltage. there was a loose nut. And so this transformer that was generating a lot of gas was due to a loose nut on that lead, and as that nut was loosening up, the resistance was increasing, and you had lots of overheating of that connection. So the nice thing here is the hydrogen monitor actually saved that transformer. This probably would have gone into a complete failure, and they would have had to replace the transformer. Okay, so I'm not sure what a 500 MVA transformer goes for these days, but I'm sure they were very happy not to have to go through the trouble of replacing it, much less the expense. So now I'm going to talk about the various technologies that are used, and we'll talk about fuel cells, probably definitely the most popular original online monitor out there. The gas chromatography, so that it is lab technology, but some vendors have monitors that are actual gas chromatographs that are able to survive in the field, and so those are very nice because they generally match lab values very closely. Then we'll talk about photoacoustic spectroscopy. There's a couple vendors out there that are using that technology, and those are also very popular. Kind of a newer technology for transformer monitoring, but not that new. It's been around a long time, but has been gaining popularity, is NDIR, or infrared spectroscopy. So we'll talk a little bit about that, and then of course we'll talk about solid state sensors or semiconductor sensors. So with the fuel cell sensor, you've got some type of membrane. Fuel cell can't survive directly in the transformer oil, so you have to separate the gas from the oil. Typically, most of the fuel cell sensors out there, you have hydrogen and CO. You have newer ones that I'm not sure how they do it, but they are hydrogen-only monitors today. But in general, the principle is you separate the gas from the oil. So the gas migrates through a membrane, and that combustible gas provides fuel for the fuel cell. They look at the voltage output of that fuel cell, and they're able to correlate that to a gas number for gas analysis in your transformer, and by watching that trend, you're able to tell if there's an active problem in the transformer. So the pros for this technology, it is a low to medium cost unit, depending on which one you choose. It's proven technology. It's been around a very long time, probably about 30 years, I'm guessing. The sensors do have to be replaced periodically. So the nice thing is customers can do that maintenance on their own. And most of the sensors that I'm aware of, the fuel cells, they do a regular health check. And so they, depending on whose you buy, I believe most of them will tell you when the sensor is bad and needs to be replaced. So the cons, typically, most of the ones out there today have measure a combination of gases, and so that might be a good thing, but you have to do a calculation based on your oil sample to see is it really reading kind of what you would expect it to. The sensors need to be replaced every few years, whether that's 1 year or 5 years, or I'm not sure how long those are lasting these days, but typically you're going to replace the sensor 2 or 3 times in a monitor's life. The other thing to keep in mind is when you make the fuel cell, there's 2 pieces of metal with an electrolytic gel in between. So the yellow stuff is an electrolytic gel. The reason that the fuel cells eventually fail is that that gel dries out over time and loses its properties from when it was a nice fresh sensor. And so if you're in a hot, dry environment, the electrolytic gel will dry out faster, and you will get reduced life of the sensors. And to the contrary, if you're in a very moist environment, your sensors, I think, would tend to last longer. Okay. So gas chromatography, again, this is lab technology. For gas chromatography, whether it's a lab or an online monitor, you still have to extract the gas from the oil. So there's various techniques to do that. The most popular in both online monitors and in labs is called the headspace method. And there's various technologies to get the gas to migrate into a headspace. Once you've separated the gas from the oil, with gas chromatography, you put the gas through chromatography columns. Those columns generally last a number of years, but most monitors on the market, if you have gas chromatography, those columns do need to be replaced periodically, although some vendors are getting much longer lives out of their columns. So there's again different variations of all these different technologies out there. So with gas chromatography, you do need a carrier gas. You need the carrier gas, which is helium most of the time. That helium keeps the all a column is it's a long, thin stainless steel tube with some kind of aggregate packed into it. So I try to simplify things. I think of those bad straws on the beach, and when you find a straw on the beach, it's packed with sand. Well, it's pretty much the same thing inside a column. They pack that sand inside the column, and depending on what types of aggregate they use, what types of sand, as the gases pass through, that aggregate separates the gases so that each gas comes out individually. You pass the gas past a thermal conductivity detector, and that's how you are able to measure the different values of each gas. And so you do have a helium bottle. This also does require ongoing calibration. So you want to check the calibration and adjust that calibration as those columns age. And so there are a couple gas bottles that are involved with gas chromatography. So the pros for this technology is it is the same as the lab. Same technology as lab technology. It's very proven. The good thing is your monitor is calibrated continuously. So there is, if you do go out of calibration when those columns are ready to get replaced, the monitor is going to let you know that. You do get excellent accuracy. And for most of the vendors out there, customers can perform their own maintenance. So vendors have done a nice job with these, and the vendor can perform the maintenance, or they can have train the customer to perform the maintenance. So the cons are, of course, it does have gas bottles, and the initial cost is a higher cost compared to other potential monitors out there. Okay, photoacoustic spectroscopy. This is also a very popular method to use in online multi-gas monitors today. The way this technology works is there's an infrared light source. That light is shined through a light filter. And once the gas is extracted from the oil, the gas passes through that gas chamber there, the analysis chamber. And when that light shines on the gas sample, there's a different light filter for each gas. So while it's looking for, say, acetylene, if there's any acetylene molecules in the chamber, those acetylene molecules will absorb the energy from that light. The light is also being passed through a chopper wheel, so that's a strobe effect, so the light goes on and off. And so when the light's on, the molecules absorb the energy. When the light turns off, that energy that was absorbed by the molecules is released in the form of a sound pulse that is picked up by microphones. And so those are very expensive microphones that are used for that technology. They're very they're built specifically for use in this technology. So you do need to extract the gas from the oil, and photoacoustics measures 6 of the hydrocarbon gases. The 2 gases it does not monitor are oxygen and hydrogen, and so photoacoustic monitors have separate sensors for oxygen and hydrogen. So the pros here are there are no gas bottles. You don't need to check the calibration on the photoacoustic gases regularly. It is a proven technology, and you get very good and reliable accuracy from the photoacoustics. The cons is generally, if you look at the specs of a photoacoustic monitor, they will specify the accuracy as found in the lab. They do use air, ambient air, as a carrier gas, and so when you're using ambient air, depending on what's in that air, it can affect the results. And so a lot of times they don't guarantee the accuracy once the monitor gets in the field. Okay, so and most of the monitors do not have the ability to check the calibration in the field, so you've got to rely on the consistency and checking your monitors against your manual oil samples in order to ensure that the monitor is staying accurate. Okay, so for photoacoustics, if you're doing the 8 diagnostic gases, or now some people are having up to 10 gases, you do have separate solid state sensors generally for oxygen and hydrogen. And typically on these, it's a fairly complex system, so the OEMs usually perform the maintenance, but I understand some OEMs are now allowing and training their customers to do the maintenance. And there is a high initial cost for the photoacoustics. Again, any of the 8 gas monitors, they are much more complex and a lot more parts to it, so they do tend to be significantly more expensive than, say, just a hydrogen monitor. Okay, so NDIR, non-dispersive infrared, or some people just say infrared. There's some different variations. This is actually the technology I know the least about, and so I hope I don't mislead anybody or say something that's not correct. But in general, my understanding is that people using this technology, there's no gas bottles required. The way the technology works, by the way, is you do extract the gas from the oil. There is a measurement done before you introduce the gas. So the measurement's done by the reference, using a reference cell. You introduce your gas into the IR cell, and then you subtract the second value from the first to come up with your result. So again, I'm not super familiar with this technology, so I do look forward to learning more about it in the future. There are monitors on the market that are using this technology. The accuracy of this technology has improved a lot over the last 10 years, and so these are becoming more and more popular. So there are pros. There's no gas bottles. They're generally, I believe, lower cost than other gas monitors, depending on the design, and it is a proven technology. The cons are it does still require a separate sensor for hydrogen. I'm not sure about oxygen on this one. I believe if it has oxygen, you also need a separate sensor for that. And I'm not sure if you can check the calibration in the field. I don't believe so, but maybe somebody can educate me on that in the future. Okay, so the other technology that is gaining popularity today is semiconductor or solid state sensors. There are a variety of sensors available. Most of the sensors available in the market today measure gas, the different gases in the gas phase. So the gas still needs to be separated from the oil. Typically through some type of membrane. Vacuum extraction is actually is being used by one vendor, and that I'm aware of and is actually yielding excellent results. But in order to measure the gas and the gas phase, again, you do need to pull the gas out of the oil, get the gas out somehow. But there are also solid state sensors that measure directly in the oil. And so this has a number of benefits. It's simpler design. These sensors, when you measure directly in the oil, can tend to last very long, very good reliability, and there's no maintenance to them. So the pros are solid state, where there is a solid state sensor available. They are generally lower cost. It's very proven technology, low to no maintenance, and sometimes they can measure directly in the oil depending on the design. Cons are that there's not solid state sensors available for all the gases. So it would be nice if you could have an 8 or 10 gas monitor with all solid state sensors, but so far that doesn't exist today. Sensors can drift unexpectedly, and so some of the things, so if you have a photoacoustic monitor, say with a separate hydrogen or oxygen sensor, chances are, from my understanding, most of the time, if those sensors start drifting, there's no way to know that sensor is drifting other than comparing it to an oil sample. And so there's no internal way to auto-calibrate. So some of the sensors do have an auto-calibration or some sort of way to check the calibration in real time. And so those sensors are, of course, preferred because you don't have to worry about the calibration over time. And so I noticed here that I'm running out of time, so I'm going to go through the next slides here very quickly. Some of the innovations I've seen is on a free breathing transformer. Typically, this is outside of North America, where you have the oil level going up into a conservator tank, and you have air above there, and it's free breathing because as the temperature goes up and down and the oil level goes up and down, you're breathing through a tube, through a breather, which is a desiccant system to keep that air dry. And so some people are now putting hydrogen sensors on that breather tube. So as the gas is coming out of the transformer, typically with a free breather, you don't want to measure hydrogen because the hydrogen will escape very quickly. But if you're actually measuring hydrogen where the gas is escaping from the transformer, then you can actually catch that, and you'll know if your free breathing transformer is generating hydrogen or not, because typically the hydrogen is going to bubble up and get up there and escape before much of it dissolves in the oil. So in a free breather, if you're going to monitor in the oil, you're probably not going to see hydrogen very often. Another innovation is on vault transformers. So vault transformers actually have 3 compartments. Well, depending on the design, some have 1, some of them have 2, some of them have 3. So there's at least one vendor that I'm aware of that is, if you're going to install monitors on all 3 compartments, having 3 monitors per transformer, you can very quickly spend more on the monitors than the cost of the transformer. So, of course, that's very difficult to justify. And so what they're doing is actually equalizing the pressure across all 3 compartments and monitoring the gas through one hydrogen sensor to tell if in that transformer any of the compartments are generating hydrogen. Okay, so it's a very innovative way to do that. Also, there are smaller solid-state hydrogen sensors available today that would allow the monitoring of high-voltage instrument transformers. So these typically only have a gallon or 2 of oil, depending on the size. But when they fail, sometimes they do fail violently, and so we're working with a customer right now that has some high-voltage instrument transformers that have been a couple have failed recently, and so they're looking at adding real-time hydrogen monitors on their instrument transformers. Okay, so from a budget perspective, again, I used to work at a utility, so I know how these things work. These are my attempts at showing a utility footprint. Each of these, it's the same footprint in both. Of course, if you like to golf, it could be a nice golfing green, but looks like there's a lot going on. Anyway, so I'm showing, well, I said 5 power plants, but there's actually 6 power plants, so should have checked my numbers there. Anyway, so you've got a number of power plants in the region, and generally with your multi-gas monitors, the first place people put those is at a power plant, because those generator step-up transformers are critical. And if they lose one of those transformers, they're going to lose some amount of generation, which can run into millions of dollars a day in losses. So those are very critical transformers, and so typically people today are putting multi-gas monitors on their generator step-up transformers. But the other transformers across their T&D system, if you're going to install multi-gas monitors, because of the expense, it's difficult to really cover a lot of those transformers. And so I took a kind of a generic case here, and I said if I had 5 power plants and 30 critical transformers, you know, those 30 I can probably justify putting multi-gas monitors on, but I might have, say, 3,000 transformers in my T&D fleet that I'd like to monitor also. But of course, I can't spend $50,000 or $60,000 per monitor to do that, because a lot of those transformers don't even cost that much. And so let's say I have a $3 million budget, and we all know that dollars don't go near as far today as they used to. So if I were installing strictly multi-gas monitors, I would, for my $3 million, say my monitor cost about $50,000, and it cost me about $10,000 to install it. So it's $60,000 per monitor installation. I'd be able to install about 50 monitors per year. But for that same $3 million, if I had a hydrogen monitor, say it's around $5,000 for the monitor, $5,000 or $8,000 or whatever you're looking at, and maybe $1,000 or $2,000 to install it. Say we're looking at $10,000 per monitor. If you had that, you'd be able to actually cover 10% of your fleet, 300 monitors, in 1 year. So you can actually make progress on monitoring your fleet for that same budget amount by installing hydrogen monitors. And of course, you'd want to look at your DGAs to see which transformers are in the worst health to put those on first. Okay, so if you're working at a utility, you know that, or working with utilities, you know that they'd much rather spend capital dollars. So utilities earn a rate of return on capital dollars spent. They are called to reduce maintenance dollars every year. Maintenance dollars usually go against your earnings per share. So if possible, they'd like to reduce the amount of money spent on maintenance every year. And so usually large expenditures can be capitalized. So if you're putting in a $50,000 or $60,000 monitor, they can spend capital money on that and make money on that expenditure. But a lot of times small expenditures under a certain dollar amount can't be capitalized. And so you would have to spend maintenance dollars. So this is a big disincentive for utilities to install hydrogen monitors. The other issue is that the typical life expectancy of a transformer is 20 to 40 years. And your monitors only generally last about 10 to 15 years. So there's another mismatch there. Even if you put a monitor on a transformer when it's new, you're going to have to replace that monitor 2 or 3 times in the transformer's life. So the industry trend is more and more utilities are starting to put a transformer monitor as a separate item of property on the books. So when that power transformer is purchased with a monitor, the monitor goes on the books as a separate item of property. So if it needs to be replaced in 10 or 15 years, that can be a capital replacement rather than a maintenance replacement. So that's a very nice thing on the being able to justify installing hydrogen monitors. And so the other thing I thought that would be valuable for folks would be to list out, if you're going to buy a transformer monitor of any sort, there's a lot of things to be considered, especially if you're going to install a lot of monitors. So what's my end goal? What data do I really need? There's a lot of complex monitoring solutions out there. And for certain transformers, you may want a $100,000 or $150,000 monitoring system, because it's going to be worth it to know, have that peace of mind that there's no issues in your transformer. But of course, as you get to smaller transformers, there's no way to justify that. So do you need different data for different transformers? How are you going to get the data? Who's going to manage that data? And if you're buying a monitor with maintenance, if there's maintenance required, who's going to pay for that maintenance? So which budget is that going to come out of? And are you going to perform the maintenance, or is that going to be the OEM performing the maintenance? Can you as a customer service your own monitor, or will the OEM need to do that? And do they provide training? What is the monitor warranty? What is the life expectancy? The big things come down to who do you trust? So some vendors, people love certain vendors, and other people can't stand those vendors. And so who do you trust for long-term and short-term support? And also, what is not only the cost of the monitor, but what's the cost of the installation? Okay, the install cost, and of course the lifetime cost of that monitor. So I am right in an hour here, so I apologize for not having time for questions at the end, but if you submitted questions, we will certainly get back to you on those. You can email me at lwhite@h2scan.com, and again, we make hydrogen sensors for these types of applications, and actually other applications as well for process and safety. But so we've got a lot of expertise in this area. So I appreciate everybody being on today. And Jeremy, do you have any final thoughts?
No, Leon, that was awesome. Tons of information, and like we said in the beginning, a recording of this will be available, and a link will be emailed to you. We will also have the link to the recording on the H2scan website. And so, no, Leon, this was great, very, very informative. Thank you.
Okay, you're welcome. And I tried to cover everything at a high level, so if you haven't figured out, I can talk about this for a long time. So if you have any detailed questions about any of the technologies, there are some that I still need to learn about, but in general, I hope I was able to adequately explain my understanding of the various technologies, and help you in your understanding of why you should consider hydrogen monitors for your transformers. Okay.
Cool.
Thank you for everybody for joining, and have a good day.
Thanks, guys. We'll see you again.